libieeep1788.
Okay, thank you for the kind introduction. Yeah, we'll talk about an implementation of the upcoming interval standard we are working on since 2008. And my talk has 4 parts. First, an introduction. And then I will talk about 2 main concepts of the new standard, flavors and decoration, which strongly influence an implementation of the standard. And yeah, the last part is conclusion about the library and the actual status of the library. Okay, I guess everybody in this room is familiar with interval arithmetic and knows that yes, there exist a lot of different kinds of interval arithmetic and a lot of different implementations which are a little bit different in some operations and so on. And this was a reason why, or one reason why an interval standard working group, IEEE interval standard working group, was founded in 2008 to unify interval arithmetic on computers and to enlarge the acceptance of interval arithmetic. And the standard specifies a lot of things, interval types of course, and constructors, literals, basic arithmetic operations, elementary functions, reverse functions which are useful for constraint propagation and so on, numerical functions, comparisons, and so on. It's a huge document at the moment, and we are still have still a draft, so yeah, it will be huge. And but now we are in a state where it is necessary or useful to have an implementation of the standard to see how it works and to have our work in progress written down on the computer. And so I started last year in winter to implement a C++ library, and I strongly use C++ 11, which is the current standard, which is quite useful for some features. And my library is mainly a framework which specifies an interface for the user, and then the backend is exchangeable really easy, like use interval arithmetic library, if somebody knows it. And there are a lot of template programming is used with template policy patterns, and it is used for type checking and mixed type operations at compile time, which is quite nice. But I use template metaprogramming, but my goal is to have an easy to use and easy to understand extendable library, and that's possible. And the third goal is it should be easy to extend because it's a framework. Okay, so that was my introduction. Now we'll talk about the 2 main concepts of the standard, which strongly influence the design of a library, or of my library, and I guess it will influence the most implementations of the standard. During our work in the working group, we had a lot of configurations of what kind of interval arithmetic we should standardize or specify. And yeah, the first question was, should we only specify classical Moore arithmetic with bounded and non-empty intervals, or should we allow unbounded or empty intervals as well? And another question was, should our interval operations purely algebraic, or should we have influence from the topology, like with C-set intervals, which use extended real numbers and compute limits of the results? And yeah, another question which was strongly discussed was, should we only support set-based intervals, or should we also include Cowper intervals, or only Cowper intervals? This was really a strong discussion. And yeah, at the moment we have the agreement that our basis or base is the classical Moore interval arithmetic, which is extended by unbounded and empty intervals to have the benefits of it. And our operations are purely algebraic. And the last part with the Cowper intervals, we have decided to have set-based as well as Cowper intervals in the standard at the moment. And this leads to the first key concept of the standard, which are flavors. flavors means that we have different fundamental approaches of intervals, completely different concepts of intervals. For example, set-based intervals or Cowper intervals. And a conforming implementation of the standard has to implement at least one of these concepts, Cowper interval or set-based interval. But it is possible to implement both, or if we decide to have a third flavor, all three or so on. But if we have more than one flavor in our implementation, the standard recommends that only one flavor is active in an execution block, which means we cannot mix Cowper and set-based intervals in one expression. In common for all flavors is that all flavors share the same set of required and recommended operations, which means for a library that says the same interface. Where it's the same interface for the user, and if we have a different flavor, the computation is a little bit different. But all flavors should extend the classical or Moore interval arithmetic, which means as long as we have bounded and non-empty intervals, the result will always the same. Only if we are outside the domain of Moore intervals, we have different results. And the Moore intervals are our common basis for our computation. And currently in the standard we have the two flavors, set-based intervals and Cowper intervals. Okay, when we try to implement the flavor concept in a library, it is helpful to have a look at the structure of the standard document, which uses a level specification with 4 different levels. So level 1 is the mathematical level, which specifies the number system of a flavor and the allowed intervals in this flavor and the operations of the F intervals. And for software design or software technique, a programmer would call this an abstract data type. And the other 3 levels, level 2, 3, and 4, are the implementation part, where we have in level 2 the set of finite intervals T and operations on this finite set of floating point intervals. And on level 3 and 4 we have the representation of the interval and the encoding in hardware and software. And this is the implementation part of the standard. And this directly influences the design of a library. And if we strictly follow this level specification, we will get something like this, where we have a set-based abstract data type on the left and the Cowper abstract data type on the right side, and each different floating point implementation is derived from this abstract data types. But this kind of design has some drawbacks. We have a lot of code duplication here and in this lower parts too. And additionally, we have not a common basis of our arithmetic. We have no common interface for both Cowper and the set-based arithmetic. So if we introduce an additional abstract data interval and the set-based and the Cowper intervals are derived from this, it looks much better, but we also have code duplication here in this part. And in time of generic data types and modern programming techniques, this code duplication is not really helpful, and it's complicated to use if we have different types for each different implementation. So it's better to introduce a generic type system. So this type is almost the same as on the last slide. Expected that we introduce a generic type T, which parameterize the interval classes, and we have only to implement one set-based implementation and one Cowper implementation. And with this generic type, it's possible to use different types for the type counts of the interval. This approach is quite good, but in the standard document, flavors are much more like policies how to represent intervals, or how operations are performed in intervals and so on. And this is not similar to this approach, but it perfectly fits onto an object-oriented software pattern called policy pattern or strategy pattern, and this is introduced here. We have an interval which is parameterized by a flavor, and the interval class only uses the flavor for the computation of the internal representations. And this is a quite good approach, and we are satisfied. It's easy to use, easy to understand, and it's easy to extend. Why is it easy to use? Here's a snippet of our library, or for the code snippet for the library. If we include the library here, and if we include one flavor, for example set-base, we can define a generic alias for an interval class, which has a generic parameter t for the pound, and we set the flavor to set-base. Then we can say, okay, we have an interval double, another interval parameterized with double x and y, and then we can compute our result in a domain-specific language matter. Quite easy. It's like on writing math on a sheet of paper. And in the next line, we use mixed type operations, which means that the result or the position of the expression is dependent on the result, and we can specify the result or the position of the result here in a generic way in the function. So it's quite easy to write and easy to understand. I said easy to understand. Another thing is our library is divided into two parts. On the one side we have flavors, and the flavors are responsible to represent the internal representation, which is done by a type def. For example, we use standard pair, which is parameterized with t and t, and it implements all operations. And the interval itself only specifies the interface, and it is a skeleton which is parameterized with a flavor policy. And then the interval class uses this internal representation by the flavor and delegates all operations to the flavor policy by moving or by using the internal representation. So it's easy to extend because the flavors are exchangeable. The interval class only uses things from the flavor, and you can exchange everything. And the intervals and the flavors then are merged together at compile time using tablet meta programming. So it's quite easy, and it's transparent for the user. The user don't see it. You only use an interval class, and other thing is done by the compiler. And it's also transparent for developers of new flavor policies, because he has only to define in his new policies the internal representation and to implement the required operations. He has nothing to do how to glue the interval class and the flavor together. Here's a short example how a flavor policy can look like. We have here the type def for the internal representation. Then we have a method constructor which gets to a lower bound and an upper bound and returns a representation. Then we have methods which gets a representation and returns a point, for example the lower bound or the upper bound. Or here we have an operation, addition for example. We get two representations and return a new representation. And in detail, we have an interval class on the right side, and every operation, for example, the constructor uses the constructor method on the left side to initialize the internal representation. And the method for add or addition uses the methods on the left side too, so it's quite easy. Okay, this was the flavor concept, and the second big concept in our standard is decorations. What are decorations? I guess everybody knows that some algorithms in math are only valid if certain mathematical properties are satisfied. For example, if you want to use the interval Newton method, which relies on the fixed point theorem for Brauer, and it is necessary that the function is continuous. And typically in interval libraries, flags are used to say, okay, this expression was continuous or not. But in the area of parallel programming, global flags are not the best decision, because you have one global flag for arbitrarily many threads. So we decided to have a decorated system, which means decorated intervals are intervals which tag with a decoration. And the decoration says, okay, it's, for example, it's continuous or not. And yeah, basically it's only a pair of an interval and decoration. And additionally, we have a propagation order for our decorations, which says, okay, this expression was at least defined, or it was defined and continuous, and so on. And this provides us a history of our computation. In detail, we have these 5 decorations in our standard. The strongest is a common decoration, which basically means that it's new arithmetic. We have an interval which is bounded, non-empty, and it's a subset of the domain of f. And f is continuous on x, and the result is also bounded. This is new arithmetic. The second one is defined and continuous, which means it's almost the same, but we kicked the bounded condition. Then we have the defined, which means that yeah, x is non-empty subset of the domain of f, so it's defined on f, nothing more. And then we have trivial, which means it's always true. And the 5th one is ill-formed, which means it's not an interval which could be generated during the creation of an interval. These are the 5 decorations. In a library, it's easy to implement with an enumeration or something else. The problem is, should a decorated interval class, which is a new data type, be derived from the interval class or from the bare interval class, like in this picture. This is a natural way how to implement it in object-oriented programming, but it has one drawback. If we implement it like this, a decorated interval is a bare interval as well. And if we have, for example, we have an interval operation which is only implemented for bare intervals, for example, a user-defined function, and we call it with a decorated interval. Decorated interval is an interval, then the bare interval operation will be called, and the computed history of the computation, the decoration, will be thrown away, and we lose all our information. And then afterwards it is possible to have implicit constructors that generates a new decorated interval and says, okay, this interval is defined or something else, so we will lose our information. So our proposal is to have 2 distinctive classes, interval and decorated interval, and then the compiler will throw an error, which we call an operation which is only specified for interval, for example. And this is the basic structure of our library. We have an interval class, and we have a decorated interval class, which looks almost the same, and they use flavors. Here's the enumeration of the decoration, and every part or every computation of the right side will be delegated to the left side. That's our key concept. Finally, at the moment we strongly work on our implementation, it's on a strong development, and we work on set-based flavors at the moment. The first flavor will be implemented with NBFR as a backend, because yeah, up to my knowledge it's reliable, we have reliable rounding. And additionally we are in contact with Christoph Lauter, who works on a library to implement the latest 754 floating point standard, and he probably will also provide functions to implement additional flavor. In future we will implement the Cowper flavors, but at the moment the specification of Cowper flavors in the standard are not finished, And our goal is to have maybe a reference implementation, that our implementation can act as a reference implementation. And additionally, to have a framework for other developers who can write flavors or other things with our framework. So that's all. Thank you.
Have time for questions?
Finally, it's a proof of concept. Do you have any performance issues in mind?
At the moment, not really. Our first goal is, with this implementation, is with an MP4 flavor, to have a reference implementation, which